Okay, hello, welcome everyone. Today we're very happy to have Manuela Kulaxizi from Trinity College Dublin, who's going to tell us about CFT, that is the stress tensor sector of the 4-point functions and black holes. So Manuela, please take it away.
Okay, thank you very much. Thank you very much for the invitation. It's a pleasure to give this Zoom talk, although probably it would be a much bigger pleasure if I were there with you. And also for being part of this common seminar between Warsaw and Potsdam. So today I'm going to discuss about some series of works on the stress tensor sector of CFT 4-point functions and their connection to black holes. So let me start by some generic statements, of course, that we know very well that the holographic principle or the AD-CFT correspondence states that some conformal field theories, or generally QFTs, have an equivalent description in terms of gravity in ADS space. So most of the aim here, the final, let's say, the big goal of my work and of where this work particularly fits in is to deconstruct, in some sense, the holographic principle in order to learn something about gravity, if possible. And questions that one might want to or hope to answer is what type of theories have a holographic description. There are some partial answers to that, or what restrictions physical consistency conditions like unitarity impose, for example, on the dual theories. And of course, since we are aiming at understanding something about gravity, obviously black holes play a special role in that, and many, many more questions. So we're going to talk about CFTs, but not any specific CFT, but rather a general class of CFTs, which we'll call holographic. And these are CFTs with certain minimal assumptions, requirements such that we expect them, or such that they may have a gravity dual descriptions. And these assumptions are such that we know from several examples. So one important thing is that we require our CFT to have a stress energy tensor operator, and we also require it to have two parameters that we take to be large, a large number of degrees of freedom, which we indicate usually by N for a gauge theory, or by C, the central charge, or rather the coefficient in the 2-point function of the stress energy tensor for the CFT. And we expect that when we take C to infinity, the CFT correlation functions factorize, for example, in this case, where we have like a 4-point function of operators, of two sets of identical operators. And gravity is described by this factorized, disconnected piece plus 1 over n squared corrections, or 1 over c corrections in this notation. Now, another characteristic scale that we expect the CFT to have is what we call a gap in the spectrum of the primary, that separates the spectrum into two classes, that of single trace of primary single trace operators with spin smaller than 2, and several higher spin operators. And here in this talk, we are going to take the gap to be infinite, strictly speaking, and play with C. So let's make it slightly more specific. What do we mean by holographic CFT? So what we call single trace primaries in this sort of more abstract setting is a set of operators that we assume our theory has, certain scalars, maybe currents, and finally a stress energy tensor, which is the highest spin operator in what we call a single trace primary sector. And then from then on, in this infinite limit, in this large C limit, what we're discussing is double, triple, multi-trace primaries that can be constructed by combining all these basic building blocks of operators with derivatives and boxes. And below, I have also listed here the standard expectation about the correlation, 2- and 3-point correlation functions, from which we will build on the behavior of our 4-point correlation functions with respect to C. And this is, of course, the leading term as C equals to infinity. These are enough for what we're going to do here, because we're going to discuss correlation functions of two sets of identical operators in this talk. So there's been a lot of progress in this context in studying these holographic CFTs. So one important result that has been obtained in several different ways is that one can study the crossing equation, and I can understand that there is a structure that is reminiscent of local gravity, and actually there is basically a one-to-one correspondence between the solutions to the crossing equation and the possible couplings that one can have in a gravitational theory, in a classical gravitational theory, and then imposing unitarity or causality, equivalent in that setting, implies that the only consistent theory that would be dual to such a holographic CFT is Einstein's theory of general relativity. That's, of course, when we tune the gap, this extra large parameter to infinity. And there's been a lot of progress in that respect. And that, of course, the progress I mentioned is in this most general setting of holographic CFTs. And of course, there is also specific discussion of specific theories like n equals 4 square Yang-Miller and equals 2 supersymmetric theories, where some of this work has been developed. Now, one question that one would like to do is go beyond this 1/c correction that gives us the leading classical gravity description. And one way one can try to do that is by studying loop diagrams, let's say in gravity, using CFT techniques. But for that, more often than not, you need to have a specific theory to know exactly what goes on. And that has been actually extensively recently studied. But what we want to do in this talk is to discuss these generic holographic CFTs, where we do not even assume, for example, supersymmetry, although we know that most of the examples have supersymmetry. And in that case, how will you try to address this question? One can think of a certain set, a class of operators that are present in generic CFTs and contribute to higher orders in the correlation function, higher orders in 1/c in the correlation functions. So what are these operators? Since we know that we definitely have a stress energy tensor in the theory, we can have building blocks, multi-stress tensor operators, that's how I will call them here, which are composites made out of the stress tensor operators with derivatives and boxes, and they're schematically represented this way because, of course, they have to be made primary. So here I have also listed what is the twist, which I denote with T. Often in the literature is also denoted with the Greek letter tau, and of these operators and their spin. And twist is basically the conformal dimension of the operator minus the spin. So this is the class of operators that we are going to, will be our objective to study. Because they give some extra contribution, and what we are actually interested in to extract the OPE data of these operators to leading order in 1/c, not 1/square root of c. I'm sorry for this typo, is 1/c. So we are interested in that contribution, but that contribution amounts to perhaps contributing to higher loop diagrams in gravity. Now, in order to address this question, the simplest way actually turns out to be to consider a 4-point function which has two sets of identical operators, but one set is considered heavy. So their conformal dimension of those operators scales with c as c goes to infinity, and the other two are light. Their conformal dimensions scales with 1. And what we would ideally want to study is the limit in which the heavy operator over c is fixed when we take c to infinity. We will shortly see why this is actually useful insofar as the study of this specific class of operators is concerned. But let's move on to point out that there is another benefit of studying this so-called heavy, light operator. I mean, in this holographic CFT bootstrap approach, that's the standard nomenclature. Maybe in people working in integrability for heavy, they denote something else, but let's keep that in mind for this talk. So the added benefit is that in the thermodynamic limit, which for us is the limit exactly that we're interested in gravity because it's the limit of a large number of degrees of freedom, we generally expect that this microcanonical ensemble description, so to speak, of this 4-point function where we have two heavy operators and two light ones is equivalent to the thermal, the finite temperature expression. So we expect that this 4-point function is equivalent to a 2-point function at finite temperature of these light operators. So that will give us some, and we know, of course, that by the CFT dictionary, a thermal 2-point function will be studied by looking at the fluctuations into a black ADS black hole geometry. So that means that we may have access to some of the black hole physics by studying this 4-point correlation function. So what is this parameter that we were interested in before, which is the delta conformal dimension of, over the central charge? This, for example, in 4 dimensions in ADS5, in terms of dual description, CFT4, it's equivalent to the ratio of the horizon radius over the ADS scale, and we will call this parameter mu in the talk. This will play an important role here. So let me just mention briefly in this introductory way, why is it most interesting to use this setup, the specific correlation, if we want the specific correlator, if we want to address the 1/c corrections to B coefficients of these multi-stress tensor operators. This is because, as you see here, if we try to look at the different, let's say, diagrams in the bulk that could contribute in ADS, at each order in mu, here we have, of course, the disconnected one. Here we have at order mu is just the exchange of a graviton. And here we have the exchange of 2 gravitons, and this one as well, where the 2 gravitons are attached to the heavy. This is basically the line that corresponds to the heavy operator. And they give contributions of this double trace of double stress tensor operators. But we know, for example, that there is some other diagram that could be of order, like 1/n to the 4th one, loop diagram that we could consider, and that's the self-energy diagram. But this diagram has only one leg in the heavy operator, and it will be sub-leading in this discussion. So by looking at this heavy light correlation function, we have this extra parameter mu, which we tune so as to access at each order in mu, double, triple, quadruple, and so on, stress tensor operators. So now let's focus on this correlator that we want to study. We want to study that analytically. And although we have a lot of assumptions and we're looking at some generic CFT, holographic, with several large parameters, this is still not trivial. And what we can do is basically study it in certain kinematic regimes. So one regime is the regio-iconal limit, where we first do a certain analytic continuation. And then we take z and z bar, it's conformal relations according to this to the position that I've placed the operators in the correlation function, to go to 1, but the ratio to be fixed. So this the limit in terms of in the gravity picture corresponds to studying a particle that is very highly energetic and moves close to the black hole. So we basically see how it's now trajectories perturbed, so how we have what is the time delay in deflection of the particle due to the fact that we have a heavy state or a black hole in the bulk. Now, so it can also be seen as a scattering problem. Now, the other limit which we can, for which we can have some analytic handle on this correlation function is the lightcone limit. In this case, the conformal cross ratios, in this case, we have a space-like separation between the light operators, and we take z bar to approach to 1 as we keep z fixed and smaller than 1. And so we put it on the light cone, approaching the light cone from space-like separation. So what we are going to focus in this talk is basically this second discussion of the correlator in the light cone limit. So let me now mention that this is a work that was done in collaboration with Andrei Parnachev and three excellent people, one postdoc, Kim Seng-Moon, and 2 students, Petar Tadic and Robin Carlson. So I've also listed here other work by Fitzpatrick, Huang, and Lee that's basically related to the work that I'm going to present here. So let me give you an outline now. So first, I think this we discussed, so we don't have to go on the holographic CFT assumptions. We'll discuss directly the correlator and how to address this light cone limit. Then we'll use the crossing equation. We use conformal symmetry to try to compute this OBE data. And then from that, maybe see how we can sum them and get some information about the full correlator at each order in mu or at fixed mu if possible. We'll discuss a lot of these results and summarize and give you some open questions. So as we said, the objective is of this talk is to study this correlator. And what we're going to do is, although we want eventually to keep this parameter mu fixed, we will address the problem order by order in mu at the beginning. And we will address it in a specific kinematic regime that we discussed, which is the lightcone limit. So below I focus in d = 4, but we'll see how and how much of these results are generalizable to higher dimensions at the end. So this is the correlation function we're interested in. This part is just the disconnected correlator, and all the information that we're after sits in this calligraphic A. So let me make a note here that in effect what we're going to focus is not this full correlator, but just the stress tensor sector of this correlator. And by stress tensor sector, I mean the sector that's based on the contribution of exactly these multi-stress tensor operators. And we will actually see that all these multi-stress tensor operators contribute equally to this correlator when this combination of this parameter mu times 1 minus z bar is fixed. So it's finite, even though we're taking let's say if we take the lightcone limit, mu is large. So, but let's go back to the beginning. We want to start the correlator at each order in mu. So we'll establish the leading contribution in both T and S channels. So what we did in most of these works is the standard original bootstrap approach, and very little we use the most recent like analytic methods like Lorentzian inversion formula. Of course, you can do that and get some mileage faster perhaps. But we'll see that there is some extra information that was needed in order to get what we wanted. So in the T channel, we have first the contribution of the identity because we have the identical operators going close to one another. At order mu, we will see the stress energy tensor and then the higher stress tensor, multi-stress tensor. On the S channel side, we will basically have contributions of this double trace operators made out of one heavy and one light operator with different number of derivatives in boxes, and how their conformal dimensions and OBE data are corrected at each order in mu. So let's focus on the T channel, which is basically contains the interesting information that we're after. So obviously the correlator in general by conformal symmetry can be expressed in this form, and here we have the product of OBE coefficients of heavy with the operator that contributes to the 4-point function times light with the operator, and this G denotes the conformal block. Again, I note here that T is the twist conformal dimension minus spin of the operator that contributes in the OBE. Now, we're interested to study this in the lightcone limit. So in this case, we have a simplification in that the blocks behave in this form, where there is an overall factor that depends on z bar, and this is to the power t over 2 times the function f that basically only depends on z, on the other parameter that we keep fixed, and it's given by this specific combination that will play a certain role later. But what we immediately see by the behavior of the block is that of all the tower of operators that of course can contribute to the OBE, in the lightcone limit, the one that gives the most significant contribution is the one that has the smallest twist, because z bar goes to 1 in that limit. And twist for unitary is expected to be positive. It's actually bounded by the unitary bounds for conformal dimensions of operators. Okay, so let's start slowly to build this up. So the lowest twist that we can ever have is just twist 0, and this is the identity operator, and that basically gives us the first contribution that's independent of this parameter mu, and it's just the product of the disconnected correlator. Now, if we don't have any additional symmetries, and since we are studying a generic CFT, an operator that we know is there is a stress energy tensor, and this will have the lowest twist because all the currents have give a bound on the twist of all the operators of spin 1 and higher, which is d minus 2 in generic dimension d. So this will provide the next significant contribution. How would that look like? It will be a product of OP coefficients, 1 minus z bar times f3, which is the function, which is exactly this function here. So it's a factor of 1 minus z times a hypergeometric of 3, 3, 6, 1 minus z. I point this out because it will be useful to remember that later. Now, what are these OP coefficients? We can completely determine them using word identity. And what we see is basically that they're proportional to this parameter delta heavy over C, or rather mu as we call it. So indeed, this contribution of the stress energy tensor comes to leading order in mu as well. And insofar, in the absence of other symmetries, don't have like supersymmetry that means that we have a stress tensor multiplet and there are the scalars and stuff, we can expect that this will be the main contribution at order mu. And any other scalar operator that even if they have some other twist, their contribution is not expected to be enhanced by powers of mu. There's no reason for them to depend on for their OP coefficients to depend on delta heavy. Now, okay, that was very easy, but now we have to address the problem of going to higher powers in mu, and there is where we start seeing the other multi-stress tensor operators that we would be generically interested in. So what happens is that basically the blocks are what they are. The corrections here to each order in mu come from the corrections to OP coefficients of these operators. And at each order in mu, we find that the lowest twist operators are those composites that are made out of the stress energy tensor operator. But here, as you see, the box is missing because this is the lowest twist that we can have from all these different families of operators, and the same goes at each order in mu to the k. So so that's it. Now how do we address this? So let's go at order mu squared and focus on this first case. So immediately we saw that although up to order mu we had just a single operator, now already the leading twist is a family of infinite operators, like of different spins, but to have the same twist. So in principle, all of them will equally contribute, and one would have to sum them up. Now, what we need in order to do the sum possibly, because we can write the conformal blocks in the lightcone limit, is to compute the OP coefficients. Now these OP coefficients where the twist is 4 for all of these operators at order mu squared, but they can have spin from 4 up to infinity, was not known. However, certain points at the time of the work that we were doing were computed holographically, so using an OPE expansion in the black hole background. And it was seen that basically all of these OP coefficients, there were like 3 or 4 numbers, I think, that were computed, had this specific form, where these were just fixed numbers in this work of Fitzpatrick and Huang. Basically, these were the people that first computed a few numbers of these OP coefficients. And you could expect that, of course, these numbers would depend on the spin of the specific operator of the same twist that you were contributing, but it was not known what was the precise behavior, what was the precise expression of A, B, and CS. So the main question is, what were these functions? And if we find them, can we evaluate also the sum and get some handle on the full correlator at order mu squared? So that's an extra thing beyond computing the OPE data of these multi-stress tensors. So at the time, what we managed basically to find out an explicit expression for all these OP coefficients, and the way we did that was to use the explicit to combine certain information. One was that there is a geodesic computation that one can do that in gravity, which is valid when the light operator has a very, very high conformal dimension. Of course, the scaling is first you take the heavy to infinity, so you have a black hole solution, and then you study the geodesic in that black hole, and that will give you effectively the correlator when delta light is very large. So if you expand this correlator around the ABS point, you'll get, of course, the 1, and then the first correction at order mu, and mu squared, and so on and so forth. But you know that that's just, and you know that this will be the expression, but say you have never computed what is sigma 1, but you don't really need to, because you know that in practice, this correction at order mu should come from the stress energy tensor, and we have computed it in CFT. It's simple. It's like this F3 that we compute. But once you know that, you also know that the same correction indicates what's the first correction at order mu squared that behaves like delta L squared, and that the other terms will only behave at the subleading orders in delta L when delta L is large. Therefore, you can immediately find out what is basically this alpha S, the number here that multiplies delta L squared in the OP coefficient, because that basically comes from the contribution of the stress energy tensor operator. And for that, you basically need an identity for hypergeometric functions that tells you that if you add them all up, you get F3 squared, basically. So beyond that, of course, we needed a few more information in order to obtain the other two terms, and that came by studying the S channel. We will say a few things about that later. And then once we got that, we had the ability to write down the OB coefficients. You see that they behave as 1 over C. There's an overall factor that is delta over delta minus 2, and these are the terms. So I just listed here just to show you that it can be done. It's nothing so important, and everything, of course, depends on the speed. Now, suppose you have these OP coefficients. The next step is, of course, you want to sum, to do this infinite sum, and to get a contribution for the correlator at order mu squared. Okay, so yeah, so that we were actually able to do, and I will show you the result later on. Let me just sketch a little bit how we were able to address the S-channel computation and convince ourselves that these numbers that we had computed BS and CS were correct. So that was again in the style of the old-fashioned, let's say, bootstrap approach. The S-channel correlator looks like this, where we said that the main contribution comes from heavy light composite operators, and we have to expand the anomalous dimensions and OP coefficients of these double trace operators order by order in mu. Again, what we will study this correlator in the lightcone limit, which in the S channel corresponds to taking L much larger than N, so much more derivatives here than boxes. And we'll also want to take, of course, delta heavy to be the largest parameter in the game. And then we'll also take Z small. So basically what this means is that we're going to study logarithmic contributions in the S channel. Effectively, that's what we're going to focus in on. So the first contribution, of course, it's trivial. It's known by the first works of Hensker, Panedonis, Polchinski, and Sally. That gives you the disconnected correlator. You can get them by using the OBE data for these double traces at the order 1, and you can compute that. Then when you go at order mu, you can find everything by knowing the T-channel contribution of the stress tensor operator, and that allows you to compute, for example, the OBE coefficient and the anomalous dimension to leading order. And then when you go at the order mu squared, you see that basically the order 1 contribution completely of the anomalous dimension completely fixes the square of the logarithmic Z term. And you can basically match this expansion to whatever you get from the T-channel correlator. Then you can do again a check against the large impact parameter in the region in the Regel limit, but perhaps in the interest of time, maybe I shouldn't go into much detail on this. Let me just say that there was a calculation in the Regel limit that can be done also in the gravitational setup. And the subtlety here is that the Regel limit basically is valid only when you first do an analytic continuation and then scale Z and Z bar to 1. While what we were studying here is the lightcone description of the correlator. In the lightcone limit, you have space-like separation and you have not taken you have done a no analytic continuation. So in order to compare the results that you get to the lightcone, what you need to do is to do some analytic continuation after you've taken the lightcone limit, and then approach gradually Z equals to 1, or basically sigma equals to 0 in this notation. So the limits are not precisely the same. That's why you can compare a couple of terms, the beginning terms and the expansion, but then there are deviations because of the difference of ordering of limits. Now, I have left that finally. All this, of course, was able because actually we were able to perform these infinite sums that I was discussing about the T-channel. So summing the contribution of all this infinite hour of twist 4, but generic spin operators. And once we performed the sum, we found the following expression at order mu squared in the lightcone limit for the correlator. So what do we see here? We see that we have an overall factor of delta L over delta L minus 2. And then we have a factor here, we have some coefficients that depend here on delta L. And some functions that are just simple plain hypergeometric functions of the form that showed up in the block decomposition in the lightcone limit. And the first term is F3 squared, then we have F2, F4, and F1, F5. So an observation that trivial observation that one can make really is that 3 plus 3, 2 plus 4, and 1 plus 5 is equal to 6. And what is 6? How does it relate to anything? So basically, it's something that sometimes it's called conformal spin. I'm not going to use that name too much because it's not so standard. It's basically the sum of the half twist plus the spin for the lowest spin operator of the leading twist family. So we have a twist family of operators which contains two stress energy tensors without indices contracted and derivatives in between. The lowest spin is when there are no derivatives and we have spin 4, and this is the operator. So for this operator, this quantity, which we call conformal spin, is equal to 6. And this dictates, essentially, the structure of the correlator in terms of products of these F functions that are basically like some conformal blocks in the lightcone conformal blocks. Obviously here we see the contribution of the stress tensor square, because if you remember, the contribution of the stress tensor is actually F3. Its block is F3. So having noticed this, we wondered, can it be that this tells us something, that we can use this structure to address higher order in mu results for this correlator? And we went on to discuss the order mu cube result. We said, let's assume that we have a similar structure where now we have products of 3 F functions, and the total the total conformal spin is 9 here, and we write all the possible products we can write with abstract coefficients A, these numbers here, and try to fix them by studying bootstrap, meaning comparing the T channel with the S channel, computing the different logarithmic corrections in the S channel. And that actually solved the problem. We were able to explicitly determine all these numbers that sit here. Now, there is, however, a little caveat. One would have hoped that these actually F functions form a basis where we can study at each order the operators, but one sees already at order mu cube here that this is not quite right, that one of these structures is equivalent to another one, and we can eliminate it. Equivalent, I mean, they're not all independent one another. There is another thing that one immediately notes, and that basically answers this remark that I made earlier on in the introduction, that what we're actually looking at here is not the full heavy light correlator, but just the stress tensor sector of that correlator. And this is the following. We immediately see that all these coefficients that show up in the correlator have this product in the denominator, which obviously blows up when the light scalar has dimension 2 or 3. This is true for a mu cube, but we have seen similar thing at order mu squared. There we had just one pole, a delta L equal to 2. So what this corresponds to is the possibility of having an equivalent contribution of the same twist, leading twist, made out of the light scalar operators that would have to be accounted for and possibly solve some sort of mixing problem in the case where the light scalar operator has one of these two dimensionalities. For example, in this particular case, I have listed here what are the specific operators. It's a double or a triple trace operator. But that actually tells us something more. Obviously, here we can assume, since we're looking at a holographic setting, that our delta L is not of this, is not equal to 2 or 3, it's not even an integer, so we don't have to solve any mixing problem. However, what this tells us is, and we can actually confirm it by going at higher orders, is that at higher orders in mu, what you see is that you have higher and higher powers of delta here. So you have poles at higher and higher values of delta. And that means that effectively there can always be a value of delta that gives you an operator of a smaller twist compared to the stress energy tensor. So now, this was all very interesting, and indeed we were able to use this technique to go at order mu to the fourth and higher. But what reminded us of was that the structure was very similar to something that was already noted in the study of the 2D Virasoro vacuum block, which gives the heavy, heavy, light, light correlator in the two-dimensional CFT case. So this correlator was exponentiates, and it has this form. It's completely known. And just basically by chance, in a sense, we were studying this correlator with respect to the phase shift computation, the Regge limit of the correlation function. And we had noted earlier with Andrei and Ginseng that if you expand it in powers of mu, you can actually write it in a similar way with all these f functions. But now, of course, the role of the stress tensor is played by the stress tensor global conformal block, which is proportional to F2. Here, there's no lightcone limit. It's just a full result for one part. So this gave us basically a lot of hope to set up a claim that the stress tensor sector of the heavy, heavy, light, light correlator has to have this form. So it's going to be, the denominator is just the usual disconnected piece. The numerator here is what comes with each power of mu that we have seen in the analysis before. And then the sum here as a sum of f functions with certain coefficients. And these coefficients are rational functions of the delta light conformal dimension. And then there was another claim that actually was related to the fact, to what we had seen in the 2D case, that there is the possibility of an exponentiation. And indeed, we checked that up to several orders. So the claim was that this correlator also exponentiates in a sense. So it can be written, and I'll explain what do I mean by exponentiation in this case. It can be written in this form, where f can be expanded now in this form, where this is the thing that actually can be kept constant to give you a correlator at a finite values of mu, where all the multi-stress tensors contribute. And these functions fk at each order in mu are given again by product of these f functions, but their coefficients now depend on delta L. This is a slight difference from the standard, from the case in 2 dimensions, where the coefficients were just numbers, as you see here. -1, 6 to the 5. So the only dependence on delta L was coming outside in front of the exponential. Okay, so let me now basically a little bit summarize and discuss also further results. So far we have shown that this ansatz together with crossing solves this crossing equation. In principle, actually, we could try to do it in several dimensions D. We have checked it in 6 dimensions as well. And in all of the cases, we could see that all the log z to the k power terms could, at order mu to the k, could be determined from the S-channel expansion. Now, we have also computed the OB coefficients, and these OB coefficients, even at order mu q, they were given as a sum of numbers. That's why I didn't list them here. And in principle, one can go higher because we have the result. It's just a matter of computer power. And they have been also checked with the Lorentzian inversion formula up to order mu cube. That's first work by Lee. Here in this setting, the Lorentzian inversion formula is used to study the specific correlator, heavy, heavy, light, light, not a light, 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 in the lightcone limit again. And we have also used it in subleading results that I will show you in a second. Now we have explicitly determined all the relevant coefficients to order mu to the sixth, and we have established exponentiation to the same order. I didn't mention anything about odd dimensions. The problem was that we tried to address this, let's say at d equal to 3, and we have some difficulties. The same difficulties have been seen when one tries to compute the OBE coefficients of this double stress tensor operators with the Lorentzian inversion formula in the work by Lee. And they point to the fact that maybe there is not such a similar structure, but I think it's too early to tell. I don't think we really worked out we can have to say we have the final word on this. It's definitely a much harder problem. One of the technical reasons is that all these hypergeometric functions, which give us the conformal blocks in the lightcone limit in even dimensions, are basically simple algebraic functions that can be written in terms of polynomials, rational functions, and logs. But that's not true whenever you look at odd dimensionality. Hypergeometrics do not simplify to anything explicit or known. And that's one problem. Another problem is the fact that the number, this conformal spin that indicates what combinations of products of f's you can have, is half integer. For example, in d equals 3 is 5/2. And that makes it a little bit harder to understand exactly what types of products you can have. Can you have all half integers, even other rational numbers? Can you have integers? What kind of products you can have from a function? Now, a natural question that one would like to do is to go beyond the lightcone limit. Beyond the lightcone limit means that we can start adding boxes to these families of operators. So this means including contribution of operators of subleading twist. So we can add boxes or we can make contractions. Basically, contractions indicate could be introducing boxes by contracting derivatives, or contractions between the t's that show up. This, for example, is for a double stress tensor operator. Let me give you an example here with a single contraction, because this is a result that I will just give you later with regard to the subleading lightcone limit. So when we have a single contraction, so when we go just one step below the leading twist operator, so the next step is to consider the subleading twist. That's twist equal to 6 operators, and there are two sort of distinct families. They're actually not distinct in the large C limit that we are discussing, except for a single operator that we'll see below. So these are the two families. One is where we have only a contraction between derivatives, and the one where we have a contraction between t. They're indistinguishable, as I said, with respect because of the large C, because they have the same conformal dimension and spin. And we can study basically explicitly how they contribute to the correlator. And the interesting thing is that we find a similar structure. So in 4 and even dimensions, we can basically set up the problem in more or less the same way as we did it for the leading lightcone case, with a few differences. And the main differences is that there are some data, some OPE data of certain of these operators that we cannot compute. And these are for operators that have spin 0 or 2 and belong to the specific families. So let me be a little bit more concrete here. What do I mean that we have a similar structure? For the case at order mu squared, so looking at double stress tensor operators of subleading twists, so we can find what is their contribution to the correlator. This is indicated here. One is go one twist below, and this is order mu squared. So this is the correlator contribution. First, there is one contribution that you see here, where the first line contains exactly the f functions that we had at leading twist, and basically the coefficients are exactly the same as the leading twist. But there is an overall factor here, and this comes from the fact that the block is correct. Because we're going beyond the lightcone, we have to add a correction to the lightcone, to the lightcone block. And then the next line contains all the contributions of this new twist 6 multi-stress tensor operators. And now you see something slightly different from before. you see that the sum of these products can be either 5 or 7. So we have two possibilities. And as we go to higher and higher order in mu, we see we have even, or to sub and sub-leading twist, we see we have even more possibilities. So, but the important point was that we can again use bootstrap and explicitly look at the S channel or use the Lorentzian inversion formula and explicitly compute these OP coefficients and find that all these B's and C's are universal in the way that was discussed by Fitzpatrick and Huang, that they depend only on the number C and the delta line, and they do not depend on other details of the theory, such as, for example, other parameters in the three-point function of the stress energy tensor, like the Euler coefficient. So we saw above that the families of operators that contribute at order mu squared are 2, although they're indistinguishable. But what we are interested in order to understand what a sum of numbers that correspond to the set functions we have to include is the bottom spin for each family of all these operators. And let's see here. So here we have these two families, they're indistinguishable, but from this one, we can make a spin 2 operator by taking away all the derivatives, and this will be the lowest spin of this family. And here the lowest spin is obviously spin 4. So if we compute the conformal spin, which is the half of the twist plus the spin of these operators, we find two values. We find 5 and 7. And that's why both of these have to be included here. Now, there is also another interesting point here, that there is one number that we're actually unable to compute. And that's this coefficient B14, which turns out to depend on the details of the theory, can be computed using the gravity, a generic gravity dual, for example, computation. And you see that if you, for example, consider a toy model like Gauss-Bonnet, it depends on the Gauss-Bonnet coupling, which accounts for corrections to the three-point function of the stress energy tensor. And you also see that this B14 effectively is the OP coefficient that corresponds to the twist 6 double-stress tensor that has spin 2. So the one that this one where you have no derivatives and there are just one contraction between the T's. Actually, this persists, as I said before, and you can see as you go to sub-leading order that using this type of ansatz and the bootstrap, you can completely determine all of these coefficients, and you can find also OP coefficients of these multi-stress tensor operators explicitly, and they are universal, except for those that have spin 0 or spin 2 and are the bottom in these families. Now, if you were to use simply the bootstrap, or for, as an example, the Lorentzian inversion formula, you wouldn't be able to go that low. You wouldn't be able to access spin, let's say, at order mu to the k below k. But using this ansatz, combining that with the ansatz in the form that I explained, you can go up to spin 2 and 0. So let me now maybe conclude with some open questions. So what is it that underlies the structure? Do we know? And unfortunately, we don't have any indication so far, although we were hoping that. But the most interesting thing would be to basically resum this series as in 2 dimensions. We have recently maybe some progress in this direction, but it's a bit early to say something on that. That comes a little bit from discussing gravity. Then another interesting question is what happens when delta L is an integer, when the conformal dimension of the light operator is an integer, specifically 2, 3, or something. You have to solve a mixing problem, and that's actually true in most of the conformal theories like N+4 that we have. And it would be interesting actually to solve this problem and see how the OP coefficients of these double stress tensors behave in that case. And then once we have these results, of course, what we would like to do is address the physics closer to the horizon. How can we hope to do that? I mean, we can we could think that we can discuss and that we can go to the lightcone limit and consider the geodesic let's consider the geodesics in black hole solutions. When we are looking at the lightcone limit, we are looking at space-like separation of the boundary points, and that gradually approach the light cone, which means that the computations that we would be interested in correspond to space-like geodesics in the bulk. And these space-like geodesics have the ability actually to probe the horizon. So this is like a limit, a regime where we're studying in CFT that can potentially reveal aspects of the horizon and confirm or rather confirm that we have we're describing black hole physics here. Another interesting thing is to take a limit. So this specific case corresponds to the spherical black hole. We can take the planar limit, and there all of these derivatives and operators are not important anymore, and we get some simplification. It would be already interesting to resum the series in that case. And once we have access to all that, of course, like some long-standing goals would be to maybe do some analytic work and understand some quasi-normal modes, or get OPE data of all these multi-stress tensor operators beyond the leading one of C corrections. So I think I will stop here. Thank you very much for your attention. Yes?
Okay, thank you very much, Manuela, for that really clear talk. So we have...
It's very technical, I'm afraid, so I don't know if it was... I tried to make it a little bit more digestible.
But I see several CFT experts in the audience as well, so...
Okay.
So we have plenty of time for questions.
Okay, so I had actually two questions.
Yes.
Maybe first one was a bit naive. So this in odd dimensions, can you actually get some mileage from gravity computation? You had some nice tricks.
Yeah, that's not naive. Yeah, I think you might be able actually to get. So that's why I said that the last word is not said yet on that. I mean, from CFT point of view and from the techniques we were using, we were not able, but maybe if you combine with gravity, possibly you can get some hint of how to proceed. Yeah.
And my second question was, so in 2D you have like an explicit square root formula for the temperature in terms of dimension of the operator over C.
Mm-hmm.
And do you have any like guesses what it might be, let's say in 4 dimensions or some higher dimensions?
You mean the square root of 1 minus 4 mu or 4?
Yeah, something like that.
Yeah, that's more complicated here, unfortunately. Yeah, I don't want to say something.
But also from gravity, one cannot guess it somehow.
Well, I mean, you can find a relation between mu and the temperature, yes, of course, and it also contains the radius of the sphere. But if you want to find this also specific parameter that you're referring to enters this full Virasoro vacuum block in a very non-trivial way and gives you the scatter-Lang numbers and a lot of things into this. So an analog of that is really lacking here so far.
Okay, thanks.
More questions?
Yeah, maybe I can ask a question. So, yes. So the expressions that you wrote down for the OPE coefficients, say 00 t squared, are they meant to hold that finite delta gap?
Yeah, it's an interesting question. I think so. I would think that this means that they're universal.
Yeah, I guess the worry is that there could be 2 statements. One is that they could, not receive any corrections in 1 over delta gap, sort of, to all orders in that perturbation theory. But that doesn't, I think, necessarily guarantee that they actually hold that finite delta gap.
Yes. So I think it's a subtle question. Nobody really has. I don't know how to access this. I mean, the the feeling is that they won't receive corrections. Now, whether they will be exactly what you said at finite delta gap, I don't know. But even that, I mean, the fact that they don't receive corrections, you expect just because we did the study in CFT and that you also did some similar study in gravity. But for example, nobody has obtained them even with the Lorentzian inversion formula for a 4-point correlator of light operators. Again, there was this heavy light operator used. It would be better if we have some confirmation from other studies. I don't know if I completely answered.
I think you
don't
did.
have. Yeah.
Thank you.
Do you have any more questions?
Sorry, so maybe I have one more.
Yeah, go ahead.
Manuela, can you say, do you see any relation of your expansion to this effective theories? Maybe work of Moshe Rosali and Felix Hell and guys when they were trying to come up with some effective action.
Well, actually, we were hoping that we could possibly use their techniques to go beyond 2 dimensions and get some mileage for this full correlator to resum basically all the steps, but that wasn't possible. So I think there is some relation, but it's not clear how to go beyond 2 dimensions or the mu there in higher dimensions.
Okay, thanks.
I'm sorry, I have a few some negative answers, but I really hope. I mean, it is actually very intriguing that there is such a structure. So it would be very unusual if one could not actually eventually resum this correlator. But it seems like a really hard problem.
All right, well, if there's no further questions, let's thank Manuela again.
Thank you very much. Thank you for the invitation and to give this talk. And I hope you all stay safe and well and possibly meet you in person soon.